back from Thanksgiving. Housekeeping, start with, there is a quiz this Friday. We will, in lieu of meeting, I've given you 60 minutes to take the quiz. Okay? And it will be open for 24 hours from the start time at 1, which would be class time. It is about 20 questions. Give or take a question, I didn't count. So it's all multiple choice. Same thing as before, you may use your book and notes. Be aware that you should practice though ahead of time, okay? Because there's some math problems and assigning orbital fill diagrams and so on. And so those things are something that need to be practiced to finish in the time window, okay? So same thing with calculation. But anyway, so December 4th, we have a quiz. And then I've been asked multiple times, are we going to do an online final? And the answer is yes. I've got some students who have acknowledged that they will be out through the end of the year. And so everybody takes the same test, then we will do that online, and I'll do it in the same fashion. I'm trying to figure out how, if you need to move that to allow you to do that. What I may do is just open up a multi-day window. Once you log in, you'll have 2 hours to complete it, and then it will close, and so that you can do it on your time. Does that make sense? Does that work for you guys? Yeah. So if it doesn't work for anyone, please let me know. And you don't have to do that here in the class, but that's the plan, so that I don't have to try to make up or give incompletes for the course. And so we've been told that that's an acceptable path for this year, so I'm going to do it in that fashion. Lab, don't forget the cyanate ion is due in lab this week. All right, we will complete another lab, which is gas laws. And then the following week, we'll do a thermochemistry lab and determine the heat of reaction for the last lab. If you do miss, then it's the same thing that I've been doing. I'll try to make arrangements to get you the lab data and then allow you to complete that. People who aren't having to come to the lab because of that, don't think you're at an advantage. By doing the lab, it gives you skills and those types of things, and you are much better off. Okay, I can say that out loud and without hesitation. So, and it's hard to figure that out. Trust me, I get some interesting questions when we do it that way, because you haven't witnessed what's going on. Does that make sense? So anyway, so just to let you know on that we will have that, the cyanate due and then the last 2 labs. And but we'll get everybody through and all the work complete. Sapling, remember, I've had a number of people who asked me to open some up over break and they got caught up, and so that's still available, but once your final passes, that's no longer available, okay? When the final deadline is over, Sapling closes and it does not reopen at that point, so just to let you know that, okay? So you should be aware of that. Anything else? Hey. Right, we're at the close. Anything important going on or anything I need to be aware of? Guys, come back to school today. All right, start studying for your finals tonight. If you've got projects due, be working on them tonight. Spend some time on them. Get the literature research done or the outline or whatever that is, and come back, because it's so easy. Right, I enjoyed my week off. How about you guys? All right, I made myself sit down and write that quiz this morning because I really didn't want to. Does that make sense? And I knew that if I were efficient and I got right back into the swing, instead of procrastinating that till Wednesday, like I could have, the Wednesday I could get some other stuff done that will need to be done on Wednesday. So I'm trying to tell you that try to be mature and come back and work. Right? Be successful, finish strong. Right. Class, we need to draw 3 possible structures, Lewis structures. sometimes more than one structure for the same three elements, possibilities, yeah. So there's three possibilities here for Lewis structures, and I want you guys to try to draw each of those conformations, right? Now, the molecule is OCN, and that's put in the order in which I want you to put the elements. So if I make a structure, is that minus sign important? It is, isn't it? Because it means that when I start counting valence shell electrons, what do I need to do? I need to add an extra one, don't I? Right, so I want you to make an attempt, right? And what's the first thing you're going to do? What's the first thing you're going to do? Count the valence shell electrons, right? And then distribute those. Try to get the octet rule to be met for each of the atoms. And there's more than one way to do that here. Okay? There's more than one way to do that. I'll give you a minute. Do it. The valence shell electrons? Yeah. Literally from the periodic table. Okay? And so carbon is the fourth element in the second period. It has 4 valence shell electrons. Okay? Nitrogen is the fifth, it has 5. Oxygen is the sixth, it has 6. Right? And then the plus 1 is what? From the negative charge. Okay? Remember, each of these be 2, 4, and you're just going to start putting those in 6, 8, 10, 12, 14, 16. That's the way I would do it. Okay? Now, the way it's drawn, the outside elements are satisfied with an octet. Is that correct? But what about the carbon? It's not, is it? Okay? So changes have to be made. What does it mean when you have this situation? When you have an element that does not have enough electrons, what should you be thinking automatically? Multiple bonds, right? Yeah. So we go from single bonding to multiple bonds when that happens. What do you guys think? We'll take a pair of electrons right there, move it to there, and that puts a double bond there, and do the same thing here. And got 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. So, bang, I got it. But there's actually 2 more possibilities. See if you can find those. And the one I've drawn is not the lowest energy form. Okay? So, we're going to learn about that today. So we can have a triple bond, right? And the lone pair of electrons 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. So right number of electrons 2, 4, 6, 8, 10, 12, 14, 16. So that matches. So we're good. So there's one more option. Have you got it? Yeah. Well, what did I do? Did I add an extra pair of electrons?
Yeah, I was like, wait a minute.
Oh my gosh, I did. I put in an extra pair of electrons. Is that easy to catch if you count your electrons? It is, because I should have how many? 16, and I had 18 on there. I just literally stuck an extra pair of electrons on there. Always check or count. I knew better. I mean, I had 5 bonds to oxygen, which is in the small part of the periodic table, and that just wouldn't happen. Okay? Can an element have 5 bonds? Yes. Okay? We moved down the periodic table period, and there are very many known examples. Okay? So, all right. So now we have 3 structures for the cyanide ion, and I want you guys to do another thing. All right, it's called formal charge, and this may seem confusing. It's not. Okay, you just have to be able to count with your fingers, is the way I do it. Cool, you guys with me? And what it says is formal charge equals the number of valence electrons on an atom. So if I start with nitrogen right here, right? If I start with this nitrogen, how many valence shell electrons does nitrogen have?
5.
5. All right. So for this nitrogen, right, the valence shell electrons equal 5, and then minus, so 5 minus, and I'm going to put a parenthesis, the number of lone pair electrons. All right. 1, 2, 3, 4. Right. Now, I'm going to count it a little. It says 1/2 the shared electrons. So I'm going to do it this way. This is the way I count. I go 1, 2, 3, 4, 5, 6. Because there's 2 electrons shared here and there's 2 here. So I do the 1/2 when I'm counting. Does that make sense? You guys with me? So this is 5 minus 6. So that equals what? That equals a -1. So for that nitrogen, it's a -1. Okay? So this carbon right here, this carbon is number of valence shell electrons. It equals 4 minus what? 1, 2, 3, 4. 4 minus 4 equals 0. So the formal charge on that carbon is 0. All right? And now the oxygen, all right? So we have our oxygen, valence shell electrons, 6 minus 1, 2, 3, 4, 5, 6. Now,
Wait a minute.
yep.
How did you get the 6?
So I counted for each bond, there's 2 electrons. So 2, 4 minus, or 2, 4 divided by 2, that's the second term, half the number of shared electrons. So I just went 1, 2 instead of doing division.
Okay.
Does that make sense?
And then you eat the number
And then I added in the lone pairs, right? 1, 2, 3, 4, 5, 6, the electrons in that. And so 6 minus 6. So this is really just knowing how to do it. This isn't hard, is it? It's just being able to identify what you're counting, okay? And so now, what I want, well, let's actually do so I'm going to write this over. This is a -1, and this is a 0, and this is a 0, okay? So on that structure, I'm putting those formal charges right there, right? I want you to do it on this structure now. I want you guys to do it and try to get the formal charge counted there. So how many did 5 minus 5 right here? No. So 5 minus 5 is 0. And how many people did 4 minus 4 here? Yeah. So that's a 0. And how many did 6 minus 7 right here? Yeah. And so that's a -1. Right? I know. It's supposed to be. It could be confusing if you don't know. And you say this is easy. If you don't know how to count, or you don't know how to build Lewis structures, right? Then all of a sudden this becomes hard. Okay, so just throwing that out there that you have to be able to build the Lewis structure to get there. And so then if I'm looking at this one, what did you guys find? Have we got there yet? Yeah? What's the nitrogen? -2. All right, what's the carbon? 0. +1. Okay, now, I'm going to ask a couple questions. The formal charge should total to the charge of the ion or molecule. Okay? The formal charge should sum to the charge or on the molecule or ion. What's the charge on our ion here? It's -1. So what's 0 plus 0 plus -1? What's 0 plus 0 plus -1? What's -2 plus 0 plus +1? -1. So the formal charge is any of these are possible. Now I want to teach you something about chemistry. This is really important. You know all this electronegativity stuff we've been talking about, being able to identify on the periodic table which is more or less electronegative. This becomes really important right here. I mean, hugely important. Because what I want to tell you is the structure that is the most stable or lowest energy form, the most electronegative element in that group is carrying the negative charge. You guys with me? Which is the most electronegative element? Oxygen, right? And so if I'm looking at these three structures, which one's the preferred structure? Which one's the highest energy form? Why this one? Because the oxygen is what? It's positive. Does oxygen want to be positive? No, not at all. Now, it doesn't mean that it doesn't resonate through this. Okay? This is a resonance form of this molecule, and it actually gives it stability, but this is the preferred structure. So you want to know how do chemists know that? Well, we know these rules. Okay? And we know electronegativity, and we can say, oh, wait a minute, that formal charge is wrong. Okay? And so, yeah, so this is a skill. Now, you'll use this in organic chemistry a lot when you're drawing structure in there. Okay? And so this is a skill that we're trying to give you the foundation for that you'll use and you'll review this in organic, okay? So anyway, and yes, I put some of these on the quiz, and you'll have to draw your structure, be able to do the count and determine formal charge. Okay, does that make sense? So I'm going to ask you guys to do that. Okay, so anyway, so this is just a table that's going through, and so this formal charge is for that structure in the top right. So that it's showing right here. In fact, if we pull up the next slide, then we can start finding the formal charge for each of those, and what you can find is that you got those correct, okay? Now, we see the same thing. This is the cyanate above, but down below is fulminate, and you notice the arrangement of elements is in a different order. The nitrogen is in the middle, okay? It's less stable that way. And so it's less stable enough that it's actually considered an explosive material, okay? You guys with me? And so anyway, and then this is calculating. So what I suggest, if you want some practice at this, is that you can look at this slide, right, with a piece of paper over the fulminate, draw the fulminate structures, and practice calculating with that. Okay, does that make sense? So just a nice way to do that. So those are included on that with those. All right. And then you guys see the oxidation numbers up there in relationship to each of the structures. And so that's something else that you can work on. All right. So what we see is resonance. Okay. Now, I'm going to give you guys a hint and tip. There's humor, sarcastic humor in this. Okay. But it's actually, there's a lot of truth to it too. Dr. Easton is going to ask you a lot of questions in organic, and if you want to be right more than half the time when he asks these questions, right, you're going to say resonance. Does that make sense? That's going to be the answer. It may sound funny, but he'll ask what stabilizes this structure. Answer me. There you go. See? And everybody got that right. Now, if it's something about the way it attacks, it's going to be steric hindrance, but that's something we'll work on when we start learning structure. Okay? But yeah, cool. Resonance. And so what it is that resonance is present when there's two or more electron dot structure that differ only in the arrangement of electrons. Are each of these structures differing in the arrangement of the electrons? Yeah. And so the resonant hybrid is an average of the structure that best represents it. In fact, we're going to learn to calculate bond order too, and we'll talk about that in this relationship towards the end of the chapter. So anyway, resonance. Resonating structures. Here's some resonating structures. This molecule, what is O3 called? It has a name. Ozone. And so there's ozone on the board. How many total electrons with ozone? Is there any charge on it? No, so it's 3 atoms. I'm going to, for clarity, can I number these? I'm going to take and just put a subscript 1, 2, and 3, right? And then I'm going to put in my resonant arrow, and I'm going to put in another 3 oxygens, right? And I'm going to label those 1, 2, and 3. Cool, you guys with me? And then what I want you to notice, well, the structure's up there, but you guys want to try to draw it without looking? Yeah, try it, don't look. Try to do your Lewis structure. There's 3 oxygens, 3 times 6 is 18 electrons, right? So it's an 18 electron system. So I've drawn the two resonant forms for ozone. Does the numbering help identify it based going from here to here? It should, right? Because what you see is that the double bond is between oxygen 1 and 2 here, right? And it's between oxygen 2 and 3 on this molecule. Now, obviously, three-dimensionally, if I flip this over, I just have the same molecule. You guys with me? Right? But what I want you to realize is that this bond can move or resonate back and forth between those two atoms. Okay? And in fact, if I mentioned the word bond order, and in ozone I have 1, 2, 3, or 2 structures, right? With 3 bonds on that, and because of that, 3 divided by 2, it's a bond order of 1.5. I have 1.5 bonds between the oxygens in that molecule. Okay? So half the time it's one place, half the time it's the other, if you want to look at it that way. That's kind of a stretch, but it helps to simplify it, right? Okay? Cool? You guys with me? So, now, resonant structures in molecules, when I have resonant structures, they give stability. Okay? And in fact, there's some molecules we can talk about, aromatic compounds. The energy from that aromatic relationship, those double bonds that resonate, it gives them a huge amount of energy that's unexpected from those types of bonds. You guys remember doing the bond energy calculations? Right? And so when I have a benzene ring, for example, then I have a huge amount of energy. How about, let's try to draw SO3, all right? SO3, there's 3 resonance forms for SO3, okay? What's going to be my center atom? Sulfur is going to be the center atom, right? It's larger, number 1. And the oxygen is going to determine that relationship. And so the sulfur is going to go in the middle. It's not going to make a ring structure, okay? How many electron system? Valence shell electrons for oxygen, 6. And for sulfur, 6. So 6 times 4 is 24 electrons. All right, I'm going to let you guys draw, at least start working on those, okay? Do you think it might have some bonding that's like this up here? Yeah, these things just start repeating when you start practicing them, okay? So when I have another thing that's going to be beat up on is the sulfur, but get my electron count right. That's really important when you're going to try to finish this, is that you have the right number of electrons.
Now, is it okay to do what you do and just put the math up, even though they aren't full shells? So that way you can just move stuff where you need to.
So this, you mean do it like this?
Yeah, that makes sense.
Well, what happens is you should redraw the structure
Yeah.
or move your electrons into place and draw the appropriate bonds and electrons. I'm gonna end up just taking a lone pair off, right? And putting a double bond right there. And so now I have 1, 2, 3, 4 for the sulfur, and everything else has, or 8, 2, 4, 6, 8. So everything is now happy. So now, in this 1, 2, 3, right? I just numbered the oxygens, so you could identify them, right? 1, 2, 3. So what's gonna happen to that double bond in resonance?
It's gonna be.
It's just gonna go from I have it on the 2 oxygen right here, so we'll move it to the 3 oxygen here. And then the last one, it will be on the 1 oxygen, and what's you? Is that COVID? Did you bring it back? So something along that line. So it resonates through those 3 structures. I want you guys to calculate formal charge, right? So each one of these oxygens with 7 things attached are -1, right? -1, -1, and this one is 0, okay? And then what's the sulfur? If I've got a molecule that's non-charged and I have 2 minuses, what are you anticipating before you ever calculate it?
It's -2, so it bounces out.
So if I have 2 negatives on the oxygens, then the sulfur is going to have to be what to balance that? Positive, and what's the number? +2. And so before I ever calculate it, you should be aware that's coming, right? And so 6 minus 1, 2, 3, 4, 6 minus 4 is +2. Okay. So just a little practice on that, all right? Formal charge, that was just for fun, or for, experience, or whatever you want to say that. Fun, not good. So anyway, so here's those molecules that we drew on the board. Now, this is showing it with lone pairs between, right? Is that okay to do it that way? Yeah, there's sometimes you'll see that in literature and those types of things, and so be aware that this is actually because it's hard to build 3-dimensional structures without a draw program in PowerPoint back when this slide was made. Think about it, right? Reality. All right. So anyway, well, I should have had you guys do that one. How about I need you guys to do a little structure for a molecule. And you guys could make a joke out of this if you're paying attention. Can you draw the Lewis structure for nitrogen oxide?
No.
Ah, good. You caught that. Please do. There's a real problem with this structure. Yeah, isn't that cool? This is a real molecule. Okay, how many total electrons? 6 plus 5? That's 11 electrons. It's called a radical. You heard of a radical before? When I say the word radical to you, what do you think of? A Biden candidate? That was a joke. Right? No, radical is someone who's on the edge, right? Well, radical in chemistry is somebody who really likes to react because I've got an unpaired electron and I don't like to be unpaired. Okay, you guys with me? So it will go attack, scavenge, whatever else to get that electron from somebody else. Okay, so it makes it highly reactive. But it still has a structure. It's still a real molecule, so try to draw the Lewis structure. Where do you think the lone electron is going to be? On the nitrogen? Yeah. Good choice.
Why on the nitrogen?
Because the oxygen is the more electronegative and will dominate in the relationship. So, yeah. It wants the electrons more. So that's where we would draw that. So. Should be a double bond. Can we have more than an octet? Yeah. Can we have more than an octet? How about PF5? So, notice I've got those. I'm letting you draw them now because you should practice. Bless you.
What was the questionable bless you?
What was it?
Bless you?
I'm sorry. I didn't mean to be quiet. Hope it's here. I'm studying.
Is it PF5?
PF5, yeah. So, how many valence shell electrons for each fluorine? 7. And how many for the phosphorus? 5. So 7 times 5 is, 7 times 5 is 35 plus 5, 40 electrons. Now, I'm going to ask a simple question. And this is, I don't want it to be too obvious, but you guys are starting to do Lewis structures and those types of things. And there's certain elements that make certain numbers of bonds, and can you use that to help you? Yeah, if I have a hydrogen always makes how many bonds? How many bonds does hydrogen make? It always makes 1, right? Now, also the halogens, now unless there was something more electronegative, right? Normally make how many bonds? 1, you guys with me? And so when I'm looking at this structure and I've got fluorine with something, right, more electropositive, the fluorine's probably going to form how many bonds? 1 bond. So at this point you have the bonding correct. Does that make sense? You guys with me? It's just you need to put in the lone pairs to make them come up to octets if you can. And which ones will have the octet? You can say it again, the same element. Fluorine, right? And so it's dominating this relationship. So fill in your electrons around fluorine and then see how many electrons you have left over. 4, 6, 8. 8 times 5 is 40. Okay? That's what we were looking for, isn't it? Yeah. So you guys can use simplifies it when you start making those connections. Does that make sense? It simplifies it, especially when you get into that world. Okay? So how about, oh, I know what the next one is. How about SF6? Sulfur hexafluoride. You guys, the Darth Vader molecule? Mm-hmm. That's the one. How many total electrons?
48.
48. Cool? You guys got this? Yeah. Just build instructions like Tinker Toys or you guys don't remember those, do you? Yeah, maybe. You? Yeah. Lego kits. This is just a slide showing some different molecules that are exceptions to the octet rule. And so anyway, so those are some of the structures that you might see. And in the next chapter, then we'll start learning the shapes of those structures and how the electron pairs help to define the position of the atoms. And so that's the next chapter. We're going to do Vesper and learn about structure. But there's just some nice examples. Any questions on this?
Yeah.
Yeah.
With, like, say the sulfur hexafluoride that
Yeah.
we looked at, considering that sulfur's valence shell is not full, the octet rule. would
It's
it be-
overfull, actually.
It's over. Oh, okay. Is that?
Yeah, so it's got, they use the expanded octet language. I don't know how that is an expanded octet, okay? I'm just gonna say that because it's no longer an octet. It is not 4 bonds or 4 things around in that relationship. There's 6 things, and so that's not an octet anymore. So that language bothers me. Does that make sense?
That does.
So it's just a different structure that's possible, and it's not possible for that first or second period. Okay, so hydrogen, helium, and now neon you might be able to force to react. I'm not sure if there's examples of that, but generally anything left of that, no, they're too small. Okay, to expand that octet as the language goes. But below that, then, those elements become large enough with enough layers of electrons that their size is big enough we can put more things around them. Okay, and so that slide that I just showed is showing you examples of different center atoms, right? Phosphorus, sulfur, fluorine, and xenon. And with those, and even xenon, what element is xenon? I mean, in terms of its family. It's over on the right, number 54, far right. It's a noble gas, right?
Yeah.
And so what do we know about noble gases? They normally don't want to react, right? But fluorine likes electrons so much that if we make the conditions right, then it will actually grab hold of a couple of the xenon electrons and hold on to those tight enough to form a bonding relationship. Okay? And so, but it's harder to do above that. And I don't know if they've ever isolated, like, for example, a neon compound. So I'd have to look at the literature to find out. but it's never been an interest of mine. Does that make sense? Yeah.
It does.
Yeah. So anyway, and then we see other elements that are larger, right, in these other compounds. And so, as the center atoms, 10 phosphorus, sulfur, bromine, and xenon. Cool. Any other questions? Good question. No? All right. So I was talking about aromatics a minute ago, okay? And I was talking about these molecules that these are special molecules. This is the aromatic we're going to talk about in this classroom. There's more examples, okay? But this one is your learning point. And I'm drawing the structure. And so I have a ring, but in that ring there are double bonds, okay? And so now at each joint there's what? We worked on this shorthand? A carbon, and there's 1, 2, 3 bonds, so what else is there right there? There's one hydrogen, and so there's a hydrogen on each of those corners to make up that bonding, okay? Now, what I want you guys to see, if I number these 1, 2, 3, 4, 5, and 6, and I draw a second structure right here, that my bonding can move 1, 2, 3, 4, 5, and 6, right? And so what I want you to notice is that the double bond here is between 1 and 2, but it's a single bond in this structure. You guys with me? And between 2 and 3, it's a double. This one's a single. And so the picture that you imagine is that those electrons between those atoms are resonating around that structure. And it gives, I'm trying to remember, we do an experiment in PChem. It's been so long since I've done the experiment, I can't remember the amount of energy that you get from that resonating double bond system, okay? But it's quite significant in terms of hundreds of kilojoules per mole, right? And so we do that by doing molecules with double bonds in them, and then doing ones that have double bonds that resonate, right, in a structure like benzene, and we find the amount of energy, and it's a huge amount, okay? So in fact, it makes it better in fuel for more energy for even in gasoline and stuff, and so the octane boost in benzene structures, such as toluenes, xylenes, and those types of molecules are all in there. And so, anyway, and not only that, they make them behave different in reactions, okay? So if you'll notice, I have a double bond and I add bromine, Br2, to that, and you see an addition reaction where the bromines actually add to the double bond, okay? But if I have a benzene ring and I try to do the same reaction, it should add, for example, on one of the double bonds, a bromine and a bromine, but it doesn't, right? What it does instead is it substitutes one of the hydrogens because of the stability from the benzene ring. So not only does it give it more energy, it changes the way it reacts. And so this structure determines function becomes really important because it changes the way molecules behave. And this will be an organic chemistry question on a test. I promise you those will set side by side and you'll have to identify that, okay? So to start learning about this early is good. I'm out of time, so we'll stop and pick up a few more slides on aromatics, and then we'll do molecular orbital theory, and we'll be done with this chapter, okay? Have a great day, guys. Good to see you.